Hello everyone, so today we'll be solving few problems related to electrostatic potential and electrostatic energy. So the first problem is, assume that an electric field 30x square I cap exists in space, then the potential difference VA minus V naught, where V naught is the potential at the origin and VA is the potential at x equal to 2 meter is. So what is given is electric field, and this electric field is only in the x direction, and we have to find the potential difference. Okay, and few options are given. I think this unit is wrongly given in this option. This should be volt. The unit of electrostatic potential is volt. Unit of electrostatic energy is joule. Okay, so first of all, to find the delta V or Va minus V naught in this case, we need a relation between electric field and electrostatic potential, and we know what is that relation. So delta V is nothing but, or if you want to find out dV, actually the formula goes like this: E in the x direction is nothing but dV by dx. Actually we are not writing y and z component, and also we are not using partial differentiation that appears in this formula, because the electric field is only given in the x direction and there are no yz component, so we are not writing them. Okay, so what is dV from this formula? Minus ex dx, or if we want to find out the change in potential, then we integrate this, and suppose this change in potential we required from point A to potential at the origin, then our integration limit will be also accordingly from origin to point A. Okay, now we will use this formula to find out the potential difference. Okay, what is Ex? In our case, it is 30x square dx, and limit is from origin, that is 0, to A is at 2 meter, so 0 to 2. Minus 30 will be taken out as a constant, and integration of x square will be x cubed by 3 from 0 to 2. We know this 30 will become 10 because of 3 in the denominator. So finally minus 10, 2 cube minus 0, or 2 cube is 8, minus 80 whole is our answer, which is option C. Moving towards the next problem. Consider a thin spherical shell of radius r with its center at the origin, carrying uniform positive surface charge density. The variation of the magnitude of electric field mod of E of r and the electric potential V of r with the distance r from the center is best represented by which graph? So let us just enlarge this graph a bit. Okay, so on there are in this graph, let us understand this graph first. On the y-axis there is magnitude of electric field. Also on this axis, this is also y-axis, or whatever on this axis is represented by this dotted diagram. Okay, so the solid lines correspond to electric field and dotted lines correspond to electric potential, and on the x-axis there is distance from the center is given since it is a spherical shape. And how for a thin spherical shape this varies electric field and electrostatic potential, that we have to find out. So for thin spherical shell, we first have to recall formulas for electric field and electric potential. So let us first draw a spherical shell over here. Okay, you can imagine this part is very thin and a charge is distributed in this thin shell. So what is the electric field outside the surface? We know if we draw a Gaussian surface from this point, okay, like this, something like this, okay, then whatever the charge is enclosed inside that Gaussian surface, that amount of charge will contribute towards the electric field at this point, and that amount of charge will act as a point charge at the center. So E of R outside will be straightforward. Let me just write down over here. So E of R outside will be nothing but 1 upon 4 pi epsilon naught. The total charge, which is it given? Now, whatever may be the total charge, let's say Q is the total charge distributed. Let's say this distance is R, then upon R square. This is the outside. So, after the radius R, if there is a point outside the spherical shell, then field at that point is inversely proportional to 1 upon R square. And you know how the R square means it is rapidly decreasing. Something like this kind of graph will be there, right? Decreasing and so on. And this decrease start from which point? This R. Okay. So first of all, we have seen the outside case for electric field. So let us see in which figure it is decreasing steeply. In this figure it is decreasing here also, and here also. Okay, let us see what is the electric field inside the spherical shell. Okay, electric field, if I draw any of the Gaussian surface inside this spherical shell, let's say over here, then there is no charge enclosed in this surface. And since there is no charge enclosed, we know electric field inside would be 0. Okay, so that means till R there won't be any electric field. Till R there won't be anything over here. Okay, so in which graph this is true? In this graph this is true, and also in this it is true. So of course option number B and option number C is not our answers. Okay, so we have done with electric fields. Let us move towards the electric potential. Electric potential at a point outside, let us check first. It is also straightforward, similar to our electric field. It will be Q upon R only and not R square. Partially because also the relation, kind of relation we saw earlier. Potential is also falling proportional to 1 upon R, is like this, not as steep as electric field outside the spherical shell, but it is falling exponentially. So in which figure? Here also we can see electric potential is falling, and here also we can see electric potential is falling. And we can say this electric field is going steeply towards the x-axis, and this is not going that steeply in both the figure. Okay, so both are potential candidate for electrostatic potential outside the, why it is constant? A spherical shell. Now let us see what happens inside the spherical shell. What formula do we have? V of R inside. Okay, now what is the electric potential inside the cell? It will be constant. Okay, why it is constant? See, electric field is 0. And what is electric field? Electric field is nothing but derivative of electric potential with respect to distance from the center. Okay, and this is 0. This must be constant. Okay, so this Therefore, electric potential inside a spherical shell is constant. Now, in which option we can see it is constant? Here also electric potential is constant. So in this option also it was constant, but we already ruled out because of incorrect electric field. So this is wrong, this is wrong, and electric potential is constant only in this case, and in this case it is linearly increasing. So this is also a wrong answer. So this will be our correct answer. So option 4 is correct. Okay, so let us move towards the third problem. Three charges capital Q plus Q plus Q are placed at the vertices of a right angle triangle, and this is an isosceles triangle. The net electrostatic energy of the configuration is 0 if Q equal to. Okay, this is an isosceles triangle. That means this side is also A, and also it is a right angle triangle. So of course we know what is the hypotenuse. It is root 2A. What is electrostatic energy? Energy stored because of the interaction between the charges present in particular system. So here three charges are present, and the electrostatic energy stored would be interaction between these three charges. So interaction between plus Q could occur. And since no charge is given to this capital Q, we will assume it is plus Q. There will be interaction between plus Q and capital Q, and also interaction between Q and plus Q. So three type of interactions will be there to calculate the electric energy stored. And the formula for electric energy is 1 upon 4 pi epsilon naught. And interaction between any two charges, let us consider first these two charges, Q into Q, upon distance between these two charges. So this distance, which is A, plus second interaction between small q and capital Q. Small q is, let us consider this one, and capital Q, then what is the distance between them? A. So the formula will be like this, plus the third term, the interaction between this and this. So it will be like 1 upon 4 pi epsilon naught q, but the distance will be root 2a this time. This configuration has the energy 0, then we have to find what is the capital Q. Okay, so let us make this as 0. You can see this part, and is common in each of the term. So what we left with is Q plus capital Q plus Q upon root 2. Okay, so this we are equating it to 0, and we have to find what is Q. So it is nothing but minus small q, Q common, 1 plus 1 upon root 2. This implies capital Q is minus Q upon 1 plus 1 upon root 2. Okay, which option is correct? Minus Q upon 1 plus 1 upon root 2. Okay, so option is not of this form. So we just have to multiply and divide by root 2. So what will happen? Minus root 2Q 1 plus root 2. Over here, this option looks correct. Okay, again multiply root 2 to numerator and root 2 to denominator. So this root 2 into root 2 will become 2Q, and here 1 into root 2 plus 2. Okay, so second option is correct in this case. Okay, so these are the simple problems that we have gone through. So thanks for watching this video. See you in the next video.